Now, one of the interesting things about being engulfed in the chemistry world is that so many things we see around us maybe remind us of something related to chemistry. Now, one of those things for me is seeing a hybrid car. Now, hybrid cars is a mixture of a gasoline and electric vehicle. It's those two vehicles kind of combined together to give us the maybe best of both worlds. Now, that reminds me of hybrid orbitals. Now, maybe not for you, I may be one of the only ones, but that's okay. And these hybrid orbitals help us understand how bonds are formed between different atoms in a molecule. One of the important things that we think about with hybrid orbitals is the fact that they are a hybrid, or a mixture of multiple different orbitals. And one of the interesting facts about hybrid orbitals is that they are a mixture or hybrid of various atomic orbitals, kind of like a gasoline and electric vehicle. There's also different types of hybrid orbitals, kind of like there's different types of hybrid vehicles. You could have kind of just a regular hybrid vehicle. You can have a plug-in hybrid vehicle that's more electric-like than a gasoline-like. And we can have something similar when we're thinking about our hybrid orbitals. Now, when we discuss our hybrid orbitals, we think about them as having different characteristics of s orbitals, so spherical shapes, p orbitals, which are kind of like dumbbell shaped, and the mixture between them. Now, the more p orbital-like they are, the more p orbitals have combined to form these new hybrid orbitals. And we label these by sp, sp2, sp3 hybridized orbitals. Now, the number of p orbitals that are combined to make these hybrid orbitals contribute to the amount of properties or characteristics that are like these p orbitals. All right, so if we have an sp hybrid orbital, that is a s orbital and one p orbital hybridized together to give us an average of those two orbitals, which gives us two new sp hybrid orbitals. Now, if I have an sp2 hybrid orbitals, that is one s orbital, two p orbitals that have combined to give us three new hybrid orbitals. We call those sp2 hybrid orbitals. And those have more p-like characteristics than the sp orbitals. Just like our sp3 hybrid orbitals, take a single s orbital, three p orbitals, they hybridize together to give us a total of four new sp3 hybrid orbitals that have an average or hybrid property and characteristics of those 3p orbitals and that one s orbital that hybridized together. Now, these properties or characteristics we think about might be the shape of those orbitals, it might be the energy of those orbitals, as well as the orientation of those orbitals. Right? When we're thinking back to our atomic orbitals, those atomic orbitals have different shapes, like our s and p orbitals. They also have different orientations, like a 2px or 2py or 2pz orbital. That would mean when they hybridize together, they're going to give us different shapes and orientations when we have an sp or an sp2 or an sp3 hybrid orbital. Now, one of the curious things we observe about these hybrid orbitals is that they really only form when we have a molecule. Now, if I'm thinking of a lone carbon atom, that lone carbon atom has the atomic orbitals of 2s and our three different 2p orbitals that are in the valence shell. Now, again, we're focusing on our valence shell because those are the orbitals that are furthest away from the nucleus. Those are the ones that are most likely to overlap with another atom to form a covalent bond. They're also usually not fully filled, so they want to overlap and form a covalent bond. Now, as we're considering these valence orbitals, especially if we're thinking of our carbon atoms. Now, our carbon atoms, as they are by themselves, have 2 electrons in the 2s, 2 electrons in the 2p. Now, curiously enough, carbon can form sp, sp2, and sp3 hybrid orbitals. It really depends on the molecule that it's in, the kinds of bonds that it forms, how many bonds it forms, how many sigma bonds or pi bonds are formed between a carbon atom and another atom. That's going to influence the kind of hybridization that we observe for that carbon atom in that molecule. So, for example, if we have something like CH4, methane, in that molecule, carbon forms 4 sigma bonds. Each of those sigma bonds form an overlap of orbitals between carbon and hydrogen. Now, our carbon atom would be sp3 hybridized because it forms those 4 sigma bonds. Each sigma bond is going to form by the overlap of that carbon's sp3 hybrid orbital with a 1s orbital of hydrogen. Now, if we go back and think, how do we identify the hybridization of our carbon atom? The way that we do that is we look at how many sigma bonds and lone pairs are sitting on that central atom. In this case, carbon has 4 sigma bonds. Each of those sigma bonds is going to form by the overlap of a hybrid orbital from carbon to our 1s orbital of hydrogen. Now, as we look at that, we see, well, those 4 sigma bonds need 4 hybrid orbitals. So those 4 hybrid orbitals that form would be our sp1, 2, 3 hybrid orbitals. Our sp3 hybrid orbitals form from the hybridization of the 2s orbital and the 3 different 2p orbitals of carbon. That's going to form a tetrahedral geometry for our sp3 hybrid orbitals, and we'll see that they have this weird 2-sided shape of these sp3 hybrid orbitals. One lobe is bigger, one lobe is smaller for these sp3 hybrid orbitals. That would mean that larger lobe can overlap with a 1s orbital to form that covalent bond. And interestingly enough, those sp3 hybrid orbitals, those larger lobes, are oriented in a way that is a tetrahedral geometry, which agrees with our observed shape of a molecule for CH4, and it also agrees with our predicted geometry that we might think of if we're looking at VSEPR. Now, if we consider another molecule that carbon forms with carbon and hydrogen, also including oxygen, would be CH2O. Now, CH2O, we'll notice as we look at our structure right here, has 3 sigma bonds for carbon, 2 to the individual hydrogen atoms, and then 1 sigma bond between carbon and oxygen. In addition to that, carbon forms an additional bond, a double bond between carbon and oxygen to form a pi bond. Now, these sp2 hybrid orbitals are less p-like in their characteristics than our sp3 hybrid orbitals. They're going to have a little bit lower energy than an sp3 hybrid orbital because they have less of the higher energy characteristics of that 2p orbital than an sp3 hybrid orbital. We notice they also have a different geometry or orientation of those orbitals. They still have a larger lobe and a smaller lobe like we see with our sp3 hybrid orbitals. Now, these are oriented in a way because of the way that they hybridize with the s and those 2 different p orbitals in a trigonal planar geometry, meaning these larger lobes are oriented towards the corners of a triangle. Now, that leads to the overlap of a carbon to a hydrogen atom with the sp2 hybrid orbital with that 1s orbital, leading to the pairing of those electrons and forming that covalent bond. Now, the sigma bond between carbon and oxygen is formed by the sp2 hybridized orbital of carbon with the sp2 hybridized orbital of oxygen. In addition to that, we form this pi bond by the unhybridized orbitals of our carbon's 2p orbital and our oxygen's 2p orbital. One important thing we see here when we form these pi bonds form not directly between 2 atoms, but they actually form above and below the internuclear axis. And we see that it's an overlap above and below that internuclear axis, which is forming our sigma bond, that forms our pi bond here. And importantly, we see that also this overlap occurs by our unhybridized orbitals. We don't see an overlap by hybrid orbitals to form our pi bonds. Now, again, it depends on the kind of bonding structure that we see for, in this case, carbon, that's going to influence what kind of hybridization we observe for our carbon atom, and has everything to do with our sigma bonds and our lone pairs. Now, the final molecule we might consider as we're thinking about the hybridization of our carbon's atomic orbitals when they form these covalent bonds, perhaps would be CO2, carbon dioxide. And we notice with carbon here in CO2, it has 2 sigma bonds and no lone pairs, and that causes carbon to be sp hybridized. Now, that leads to 2 unhybridized orbitals being left for carbon with those 2 sp hybrid orbitals. Those 2 sp hybrid orbitals, again, kind of like our sp2 and our sp3 hybrid orbitals, are going to have a larger lobe and a smaller lobe. Now, in our carbon atom, as it forms the bonds between carbon and oxygen in CO2, each of those carbon-oxygen bonds are oriented directly apart from each other, or perhaps in a linear fashion. We observe that that's because our sp hybrid orbitals are oriented 180 degrees apart from each other, or the larger lobe is facing away from the larger lobe of the other sp hybrid orbital. And that is why we observe our oxygen atoms forming bonds with our carbon atom in a linear fashion. That contributes to the overlap between our carbon and our oxygen atom forming our sigma bonds. Now we notice that our carbon has two unhybridized orbitals. Those two 2p orbitals are going to form covalent bonds between carbon and oxygen, not as sigma bonds, but as pi bonds. Again, those pi bonds are above and below the internuclear axis. We think back to the orientation of our carbon atom and the orbitals present in our carbon atom. We can think of one of the 2p orbitals going above and below the carbon atom and one going forward and backwards between the carbon atom. That's going to lead to an overlap of that unhybridized orbital between carbon and oxygen above and below the sigma bond for maybe our oxygen on one side, and then in front and behind the sigma bond between the carbon and oxygen for the other oxygen atom. And again, that leads to two sigma bonds, one between each carbon and oxygen atom, and two bi bonds, one between each carbon and oxygen atom, to form our double bond between each of our oxygens and our carbon atom. Now we can think about our hybrid orbitals connecting back to maybe our hybrid vehicles, right? When we're thinking about our hybrid vehicles, it's a combination of a gasoline and electric vehicle. Just like when we think about our hybrid orbitals, it's a combination of different types of orbitals, our s orbitals and our p orbitals hybridizing together to form sp2, sp3, or sp hybrid orbitals, as we thought about our example with carbon. Now hopefully that was helpful as you consider the way that you might connect hybridization to our valence bond theory, considering how orbitals overlap between one atom and another to form a covalent bond. Now, as we saw for carbon, the hybridization of that carbon atom is not always sp3 or always sp2 or always sp or maybe always never hybridized. It has everything to do with the molecule that that carbon atom is in, the kinds of bonding it forms, whether or not it's going to form multiple sigma bonds, what kinds of pi bonds we observe for that carbon atom. And we only use carbon as an example. We'll see that this hybridization is true for any other atom we might consider, nitrogen or oxygen or sulfur. Right, we can consider the hybridization of each of those atoms just like we might with our carbon, but it has everything to do with how many sigma bonds and how many lone pairs are around a central atom to influence what kind of hybridization we observe.